Advanced Functions. Grade 12. Unit 1. Functions. Characteristics and Properties. Skills and concepts you need. In this video we will look at factoring a quadratic expression in one variable, finding domain and range of a quadratic function, as well as some operations with zero that you should know. We will treat all variables as real numbers. Complex numbers are not covered in this video. Evaluate f of x equals x squared minus 2x plus 4 for each of the following values: a, f of 0, b, f of x minus 1. You can pause the video here and try to do it yourself. To evaluate f of any variable z, replace x with z in the equation. Solutions. A, f of 0 equals 0 squared minus 2 times 0 plus 4. 0 squared is 0. 2 times 0 is 0 too. So, we get f of 0 equals 0 minus 0 plus 4 and f of 0 equals 4. The answer to the question A, f of 0 is equal to 4. B, f of x minus 1 equals x minus 1 squared minus 2 times x minus 1 plus 4. X minus 1 squared is x squared minus 2 times x plus 1. 2 times x minus 1 is 2x minus 2. We get f of x minus 1 equals x squared minus 2x plus 1 minus 2x plus 2 plus 4. And this is equal to x squared minus 4x plus 7. The answer to the question B, f of x minus 1 is equal to x squared minus 4x plus 7. Factor the following expression: 5x squared minus 16x plus 3. You can pause the video here and try to do it yourself. First of all, note that not all quadratic expressions can be factored, but usually the expressions you see in tests are chosen so that they can all be factored. We will present two approaches to solve this problem. In the second, we will show how to determine whether an expression can be factorized or not. Solution 1. Let's write minus 16x as minus 15x minus x. Here we can see that both 5x squared and 15x have 5x as the common factor, and now we can present them as 5x times x minus 3. Next, we can put x minus 3 into a bracket and add a negative sign in front of the bracket. Here again, we see a common factor, x minus 3. Now, the original expression can be presented as a product of x minus 3 and 5x minus 1. This is our final answer. Solution 2. The general form of a quadratic expression in one variable is x squared plus bx plus c, where a, b, and c are arbitrary constants, or parameters, and a is not equal to 0. To find possible roots of the expression, we need to solve a polynomial equation x squared plus bx plus c equals 0. The discriminant is used to find the nature of the roots. The discriminant formula of a quadratic equation is b squared minus 4ac. The quadratic formula in terms of the discriminant is x equals minus b, plus minus square root of the discriminant, and all these divided by 2a. If d is greater than 0, the quadratic equation has two different real roots or zeros. If d is equal to 0, the quadratic equation has two equal real roots or zeros. If d is less than 0, the quadratic equation has no real roots. If d is equal to or greater than 0, the quadratic expression can be written in intercept form, the product of a, x minus the first root, and x minus the second root. When d is equal to 0, the roots of the quadratic expression are the same, and the intercept form will be the product of a and x minus the roots squared. In our expression, a equals 5, b equals negative 16, and c equals 3. Let's evaluate the discriminant d. The discriminant is equal to 196. The discriminant is greater than 0. It means the quadratic equation has two distinct roots. A square root of the discriminant is equal to 14. Now we can evaluate the roots. The first root is 3. The second root is 0.2. Now we can use the roots to complete the intercept form for the original expression. Here we have the same result. The expression is written as a product of x minus 3 and 5x minus 1. As you noticed, the first method we use here is faster and easier, but this is not always the case. Sometimes the long second method may be shorter than the first. Sometimes it is useful to look at the sum and product of the roots of a quadratic equation as a system of equations. The equations are easy to prove using the quadratic formula for the roots. Here's a modified form that will help you calculate the roots even faster. Let's try. We need to find two real numbers p and k so that their sum is 16 and their product is 15. 1 and 15, right? Now find the roots by dividing p and k by a. The roots are the same as we got in solutions 1 and 2, so the intercept form of the quadratic expression will be the same. The last thing I'd like to show before moving on to the next topic is an alternative way to determine whether a quadratic equation has roots if you decide to use the first method but don't want to calculate the determinant. We can write the equation in vertex form, product of a and x minus h squared plus k. We need to pay attention to k and a. If k is 0, then the equation has two equal roots. We say the equation has a double root. If not, look at the signs of a and k. If they have the same sign, both positive or both negative, then the equation has no real roots. And finally, if a and k have opposite signs, then the equation has two different roots. Let's implement this method. Our original expression can be written as 5 times x minus 1.6 squared minus 9.8. Minus 9.8 is not equal to 0, it means the equation does not have a double root. A is a positive number, k is a negative number. Thus, the equation has two different roots. Finally, let's look at the graph of our function, written in vertex form. If you are given a standard or vertex form of a quadratic, the sign of your a value tells you the opening direction of your parabola. If a is positive, then the parabola opens up. If a is negative, then the parabola opens down. The parabola of our function opens up, its vertex is at the point 1.6, minus 9.8. It crosses the x-axis twice, so the quadratic equation has two different roots. Let's change the sign of k to the positive 9.8. The parabola still opens up and looks like the original one, however it does not cross the x-axis, and the quadratic equation has no real roots. Now change k to 0. You get the same parabola with the vertex on the x-axis. The equation has a double root. Now it's time to move on to finding the domain and range of the quadratic function. State domain and range of the function. F of x is given as x squared minus 6x minus 10. You can pause the video here and try to do it yourself. First of all, remember that the domain of any polynomial function is all real numbers from negative infinity to infinity, since polynomials consist only of operations that do not involve any restrictions. So, the first part of the question can be answered right away. The domain of the given function is the set of all real numbers. However, the situation is different with the range of polynomial functions. Here again, we look at two approaches to solving the problem that you should know, and touch on another very interesting method not covered in Unit 1. Solution 1. From the previous topic we know that the graph of a quadratic function is a parabola. We also learn how to determine the opening direction and the y-coordinate of the vertex of our parabola. If a parabola opens upward, then it has an absolute minimum. If a parabola opens downwards, then it has an absolute maximum. The value of this maximum or minimum is equal to the y-coordinate of the vertex. Now what remains for us to do is to write down the quadratic expression in vertex form and take a closer look at the sign of a and the value of k. Our function written in vertex form will be f of x is equal to x minus 3 squared minus 19. A is positive 1, k is minus 19. The parabola opens up, and minus 19 is the minimum value of f of x. So, the range is the set of real numbers where y is greater than or equal to minus 19. Solution 2. The second method is based on the fact that our parabola opens up and crosses the x-axis twice, and the x-coordinate of the vertex is halfway between the two roots. We can find it and evaluate f of it to get the absolute minimum of the function. You can pause the video and try to do it yourself. Let's remember our system of equations from the previous topic. What was the sum of the roots? Minus b divided by a, right? Our a is 1, b is minus 6, so the sum of the roots is 6, right? The half of 6 is 3, that is x-coordinates of the vertex. Next we will find f of 3, this will be the minimum of the function. F of 3 is equal to minus 19. The problem is solved. We got the same result, the range of the given function is the set of real numbers, where y is greater than or equal to minus 19. Now let's move on to the last method. It is based on derivatives of a function. The derivative of a function describes the instantaneous rate of change of the function at a certain point. Another common interpretation is that the derivative gives us the slope of the line tangent to the graph of the function at that point. The derivative of the function at the turning points, vertexes, is equal to 0. These points are also called extrema of the function. Let's take a closer look at the graphs of our function and its derivative. So it's clear from this graph that it is enough to find the point where the derivative graph intersects the x-axis, and this will be the x-coordinate of the vertex we are looking for. To find the y-coordinate, we simply find the value of the original function for that x. You will need to remember the following rules. The derivative of the sum of functions is equal to the sum of the derivatives of each of these functions. The derivative of x raised to the power of n is equal to the product of n and x raised to the power of n minus 1. In other words, we borrow the power of x and make it the coefficient of the derivative, and then subtract 1 from the power. Now you have enough information about derivatives, and you can continue further on your own. If you agree with this, you can pause the video. The derivative of x squared is 2x, the derivative of 6x is 6, and the derivative of any constant is 0. Our derivative function is 2x minus 6. Let's find the zeros of this function. The equation gives us 3 as the root. 3 is the x-coordinate of the vertex. F of 3, which is minus 19, is the minimum of the function. So here we have the same result again. The range of the function is the set of real numbers where y is greater than or equal to minus 19. Let's try another tricky question. State domain and range of the following function, fx equals x minus 2, divided by x squared minus 6x plus 8. With any rational function, be aware of division by 0. Set the denominator polynomial not equal to 0 and solve. The denominator can be written as a product of x minus 2 and x minus 4. Values 2 and 4 must be excluded from the domain, because if is either 2 or 4, the denominator will equal 0. Division by 0 is undefined. Therefore the domain of the function is all real numbers except 2 and 4. Now we can simplify the fraction and write the original function as fx equals 1 divided by x minus 4, where x is not equal to 2. The function has a discontinuity at x equals 4. Since x can't be 2, the range of the function has a hole at y equals minus 0.5. The ranges also exclude 0, since fx gets close and close to 0 when x increases toward positive or negative infinity, but never reaches that value. So, the range of the function is set of all real numbers except 0 and negative 0.5. We have found out that if a parabola intersects the x-axis, then the x-coordinate of its vertex is minus b divided by 2a. But what if the parabola doesn't intersect the x-axis and we still need to find that coordinate? Can we use the same formula? The short answer is yes. Although we initially assume the existence of real roots, the formula for the x-coordinate of the vertex of a parabola should remain true even if the parabola does not intersect the x-axis or just touches it. Let's see how it turns out. Here I would like to note that mathematically this fact can be written in the following form. In the first bracket, there are conditions for fulfilling the statements. In the second bracket, the sign before d means for any. For any real positive d, x0, the x-coordinate of the vertex, is equal to minus b divided by 2a. First, we will consider the case when the parabola touches the x-axis. and then we will move on to the situation when it is completely above or below the x-axis. When the parabola touches the x-axis, the value of the discriminant is 0. So, the first question is, if d is 0, what x0 is? We know that when d is 0, the function has a double root. The double root value is the x-coordinate of the vertex. Let's remember the formula for calculating roots. Since a square root of 0 is 0, we get x0 is equal to minus b divided by 2a. So, the statement about the x-coordinate of the vertex is true when d is equal to 0. Now the second question, what is the value of x0 when d is less than 0? We will have to step outside the set of real numbers for a moment and note that when the discriminant takes negative values, the roots, although not real numbers, exist in the complex plane, and their sum is equal to the real number, negative b divided by a, since, when we are adding the roots up, we get rid of the imaginary part of the complex number. Let's imagine that the discriminant d is a negative real number, denote the square root of d by z, and look at the sum of the two complex roots divided by 2. Here we get the same result, x0 is equal to minus b, divided by 2a. Now we can say that the x-coordinate of the vertex does not depend on the value of the discriminant, and it is equal to minus b, divided by 2a, for any discriminant d. The y-coordinate of the vertex is equal to the f of its x-coordinate. So we can write the coordinates of the vertex as x0, y0, is equal to minus b, divided by 2a, and f of minus b, divided by 2a. Let's remember the vertex form formula from the previous topics. F of x is equal to the product of a, and x minus h squared, plus k. X minus h squared is always greater than or equal to 0. It gets its minimal value when x equals h. If a is less than 0, the product of a and x minus b squared is always less than or equal to 0. Therefore, if we add k to it, it will be less than or equal to k. So, the function reaches its maximal value when x is equal to h, and the maximum value is k. H and k are the coordinates of the vertex of the parabola defined by the function. Now we can map the h and k values to the x0 and y0. H is minus b divided by 2a, and k is f of the value we just assigned to h. Let's see what we get if a is a positive number greater than 0. When a is a positive number, the function has a minimum, which is equal to f of h, and that is k. Here we get the same result after mapping h and k with x0 and y0. The only difference is that when a is a negative number the vertex is the maximum of the function, and when the opposite, it's the minimum of the function. Since we know the values of h and k, we can use them in the vertex form of our function and write a formula to convert the standard form to the vertex form. Let's write down this formula, which will help us quickly convert a function from a standard form to a vertex one, and try to implement it. Write the function f of x equals 4x squared, minus 16x, plus 2 in vertex form. Solution. A is 4, b is minus 16 and c is 2. We need to evaluate b divided by 2a and f of minus b divided by 2a. We get b divided by 2a is equal to minus 2, and f of 2 is equal to minus 14. The function in vertex form will be 4 times x minus 2 squared, minus 14. Now it's time to move on to the last topic about operations with 0. Everything here will be in the form of short questions and equally short answers. Let's start. 3 divided by 3 is 1. 2 divided by 2 is 1. 1 divided by 1 is 1. What is 0 divided by 0? It's not defined, it's a restricted operation. 2 factorial is 2 times 1 and equals 2. 1 factorial is 1. What is 0 factorial? 0 factorial is defined as 1. 0 power 2 is 0. 0 power 1 is 0 2. What is 0 power 0? 0 power 0 is defined as 1. What is square root of 0? Square root of 0 is 0. That's it for this video. The next video will cover units 1.1, 1.2 and 1.3.